You guys see those problems that weren't straight up, they were really not straightforward at all. That's what sucks about this is really cool to get the idea, but then it gets to be almost too easy. And some of you guys are like, I'm not there yet, but. And then the minute you give a little more interesting function, it gets like insanely hard. So, yeah. But it's a nice little baby step into proof stuff. Okay. Where to now?
What's the definition of a derivative?
Oh. So the definition of derivative. Of f of x at x equals a. I can write it two different ways. It's just in fact, very often I'll call it the limit definition of the derivative. Right?
Isn't it f of x?
Well, it's the same old shit we keep using. At x equals a.
Oh,
Yeah. It was either going to be this guy, right? This good old guy. Or you can write it like this. These both are mathematically equivalent.
And derivative is slope, right?
Slope, kick ass. Derivative is rate of change of thing.
Okay.
So my function is the number of strawberries growing. The derivative would be like if I did the number of strawberries that I see per day, right? So each day. So the number of strawberries on Monday, the number of strawberries on Tuesday. That's my function. The derivative would be the number of strawberries per day. So the rate of change of number of strawberries per day. Derivative is slope, and slopes are ratios. So that's why I can write this like that. That's what that is. That's the symbol for derivative. Or I can write this. Well, this gets a little bit weird, but if I have f of x, I can write f prime of x, or I can write this as df dx. Change in f over change in x, which is slope. But what's better about this is whatever the units on f are and whatever the units on x are, sum of the units on my slope, right? So if f is number of strawberries and x is time, this is number of strawberries per time.
So what do you do with the d? Is that just supposed to?
No, you don't do anything with it.
Right.
This
It's
means
just telling you that it's
the
a
change
derivative?
in f.
Okay.
And what's different, so this means the change in f also, but this could be a big step. This is an infinitesimally small step.
Okay.
Yeah.
Because the book only has the triangle, which is that, what is that, delta? The
Yeah,
triangle?
but trust me, they will have this too.
Well, so far it's only been the triangle,
Okay.
in chapter 7, or
Are
in
they
2.3.
interchangeable?
No, not really.
No.
Because again, this is a gross step. Gross meaning big.
So how do you know which one to use?
The problem will be very
The problem
explicit.
will have,
This would be related to an average velocity over a set of time, and this
Okay.
would be instantaneous velocity, for example.
okay.
Yes. Average velocity, you just kind of take stuff close to the point you're interested in. Instantaneous, you better get exactly that one point, and then we need calculus to help. So this is algebra, this is calculus. And some of you guys, your teacher in algebra, some of you should have seen that, right? That means change in y. y2 minus y1 is how much y changed. So the symbol means change in, big change. This means infinitesimally small change.
Oh, sorry, you said the big one is average velocity over time, and the small one is what?
What?
The d, small
Oh.
d. You said.
Where are we at? Sorry. All right. Yeah, this would be average velocity over a range of time.
Right, and the other one is?
This would be instantaneous
Oh, that's right.
velocity at a certain time. So let me see. So the whole thrust of a lot of the problems in chapter 2 were taking this idea, letting delta x get smaller and smaller, right? If you think about it, isn't that what it did? You'd have to do step in, you'd see the pattern, and you make a guess for the derivative at that point. That's what all the section 2.1 problems basically did to you. Okay, it just did. Nobody's agreeing with me, but oh well, if you did the homework, that's what it did to you. So if I let that get really, what I do is it becomes this. So this limit, if I let that delta x, if I let it get really tiny, let h go to 0, let x go to a, either way, what's going to happen is I'm going to get the instantaneous whatever right at that point, the instantaneous rate of change. That's what that means. So that means big steps, that means incredibly, impossibly small steps.
So we know that because x is going to 0?
X is not going to 0.
X approaches 0? Is that how we know that we're going to from big to
Yeah. If I
to
let
small?
this step get really small, then I'm going to small steps. Yeah.
But if it was x approaches 20, then we would keep it in the same.
Yeah, you wouldn't really see that. This is a statement you would only see when you're trying to define what that is. That is this process taken to the extreme. And think back to section 2.1. What did they make you do? They made you do 1 to 2, 1 to 1.5, 1 to 1.1. What are they doing? Making the delta x get tinier and tinier and tinier. And what was your guess going to be? The instantaneous rate of change of whatever. So this is basically how to summarize section 2.1. How important is this kind of idea in nuts and bolts problems? Not. The minute I say that, some students go, why the shit did you tell us that? Because what's the most important thing? Ideas. I understand there's a nuts and bolts, how do I get through this problem, versus an idea. The better you understand the idea, the better you understand the nuts and bolts. Period. All math. Okay, where else do we want to go? Did I finish that one? What was the question?
I just asked you to define derivative.
Oh, yeah. See, I can just go. All right. Oh, yeah, that's right. That get us here, and then that get us there. Okay.
Because in those ones, we basically just do the same as how we were doing before, just find the tangent line of whatever the...
Yeah. Are you looking at a specific
so
problem?
8, basically. So
In
it
section
says-
2.7?
Yeah.
Oh, yeah.
Practice,
Oh, on the test, practice test.
it says to find the derivatives with the definition of a derivative.
Okay. I'm glad you're saying this. I can't remember if I said this last time. So we didn't get through 2.8, right? We didn't get to section 2.8. Number 8 would be a 2.8 problem. Yeah. Because what am I missing in number 8? Look at number 8. It says find the derivative using definition of derivative, right? Number 8. What's missing there that we have to have for section 2.7?
The limit?
No. A point. So 2.8 says, let's just do the derivative everywhere. Let's not make a specific. It's like that one example we looked at where they just kept it as a. Wouldn't that be more powerful? I mean, so that problem we did earlier with the 7 minus x plus x cubed, is that what it was? Right, wasn't that the function we used earlier? And we did it at x equal negative 2, was it? I don't remember. 1, whatever. And we did the whole process, right? The whole limit is f of x, and we did the whole, and then that's number 1. And number 2 says, okay, what about x equals negative 2? And then we do the whole process. And then number 3 says, what about x equals 4? And then we do the whole process. Oh, shit. Wouldn't it be better to do the whole process, just leaving a in there? And then we know the answer for any value of a. That's what section 2.8 does. That's what number 8 is actually asking you to do. I'm not going to put that on the test, though, because officially we haven't gotten to 2.8 yet. But I love that idea. That really gets at the heart of why we do shit like, who knows what this is? F and C should give it away maybe in 32 degrees. I just gave it away. Fahrenheit and Celsius. Why we do shit like solve for C, right? This equation is good if I know C. If I don't know C, this equation sucks. If they're like, find C if F is 7, if F is 22, if F is 848. Wouldn't I rather just solve for C once and then plug all that shit in there for each problem? Instead of solving for C every single flipping time. This is what algebra did for you. It's what students balked at, but then you guys didn't realize, That's really good to know how to do. Shit. Makes every problem after that quick. And if you're going to be any computer programmer, you know you want to be able to do this once so your program is tight, doesn't take as much time. Fortunately, a lot of lazy-ass computer programs out there, but be better than them. All right, let me see. Did I was going to go back and make sure I actually answered the question. What were we looking at? Oh, yeah, number 8.
Yeah, we don't
Okay.
even know.
So that kind of question, I would say find the derivatives of the following at x equals 2 or something, right? I'd have to give you that because we didn't do 2a yet. And then you would do the stuff we did earlier. I might put that as a bonus problem, maybe just to see if you want to try it. So number 9, you could do number 9. Right? If I would just say find the tangent line to this function at that point, then you do exactly what we did earlier.
What is that first part of the sentence being understand?
Using what you found in number 8?
Yeah, what would we have found in number 8?
Look at 8a. Isn't that the function in number 9?
Oh, okay.
So you would have found the derivative at any point, and then you would just have to plug -2 in. And out would pop the number that's the slope. We can't quite do that yet, officially. So I won't ask you number 8, but I will ask you number 9. And on the answer key, you can see how number 8 looks if you want to. Or don't look at it if you don't want to. Every other problem on here could be on the test. I think number 8 is the only one that was from section 2.8.
I had a question on the 2.1 homework 4A.
Okay. So these kind of problems have a couple levels to them. They all ask me to find slopes. So my first instinct should be I got to get 2 points so I can find a slope, right? Because 2.1 is before we really got into the full power of calculus and limits and all kind of stuff. So the function they give you, number 4, is this guy, right? And then they ask you, for example, oh, and the point P is, where'd it go? 0.50. And does that point make sense? When x is 0.5, what's cosine of pi over 2? Even if you don't know, you can just say 0. But yeah, cosine of pi over 2 is 0, because that's y. Cosine likes x. It's not going to like it here. That's why it's better to know cosine likes x, sine likes y. Everything makes so much more sense. SOHCAHTOA sucks. It really does. It does not get you very far. Anyway, sorry. So like part A, number 1. Where'd it go? There it is. If Q is the point, x cosine, so Q is x cosine x pi. Yeah, PQ. So number 1 says let x equal 0. P is going to be this for every single one of these problems. So I got 1 point already. So I want to find slope between 0.50 and 0 something. Every single one of these is going to be just figure out the other point and then get the slope like you always would. So 2.1 is algebra. 2.1 is pure algebra. So how do I get this piece? Plug a 0. What's cosine of 0? 1, because it's where it likes it. Cosine likes x. It's on the x-axis. It's going to be really freaking happy. The happiest it could be. And now you just find the slope. y2 minus y1 over x2 minus x1. So step 2 says, where'd it go? X equals 0.4. So now I want to find the slope between 0.50, always, and 0.4, I don't know yet, right? Plug a 0.4 in, get what it is, find the slope. You guys see that? So 2-1 is pure algebra. It's just getting the other point that we don't know, at least on that problem. They're all similar to this. Once you get 2 points, you can find this. Once you get 2 points, you can find this.
Yeah, I'm pretty sure I was overthinking it, because I did the 2-1 homework after we had started covering other.
Oh,
topics.
shit.
So I looked at it and I thought I was supposed to do.
So the further you get in math, and this is true for algebra too, but you'll learn other shit that comes that really messes your brains up. But you got to remind yourself, what do I know right now? You know, yeah, you're right. You got to separate it out from what we talked about later. Very truthful. There's no explicit limits in 2-1, but you can see the idea of limit in 2-1.
Question, section 2.2, question number 21.
Oh, okay. So this one wants you to make a table to investigate this limit. Where do you go first? Right, and then they give you, so they're going to approach 0. They give you 0.5, 0.1, where'd it go? 0.01, 0.001, 0.001, I think that's as far as they go. Yeah, and then the negatives of those. Negative 0.0001, negative 0.001. Does this not look familiar, right? So I like to set it up like this so I can see as I come from the positive side, as I come from the negative side, I can make my guess. So plug that in, put down the answer. Plug that in, put down the answer. Plug that in, and then see where they're going. That's the whole idea of limit, right? As my inputs get closer and closer to 0, what are my outputs doing? That'll be the answer for the limit.
That's the same way we do number 12 on the.
Is that cool for that one? Yeah. 12. Yeah, 12's the same way. I ask you to make your own table of values for number 12 on the practice test. What number am I trying to approach? Pi over 2. By the way, I'm pretty sure I showed you this, but let me show you this one more time. Get you. The beast awakens. I want to show you something really, really cool. So 12, it's going from, it's approaching pi over 2, right? So, do I want that one or do I want this one? I want this one. What is happening? Poor little dude. This should be right. Do it. Yes. Try to approach pi over 2. So how do I make the table? Sort of like I did here. This was approaching 0, so that was relatively easy. Now I want to approach pi over 2. I think it's just from one, no, from both sides. So how the hell, how do I set this table up? One way you can do it is, what is pi over 2 roughly? What's pi roughly? 3.14. What's half of that? 1.57. So you could go 1.5, 1.55, 1.57, right? But to be honest, I want to show you something better you can do. You ready? You can just do pi over 2 minus 0.1 pi over 2 minus 0.01. Do you see that? Am I getting closer to pi over 2? Yes. You're like, yeah, man. And on the other side, it would be plus those, right? So here's how I can use the calculator, this silly little computation monster. Put the thing in here. What is it I'm working with? Cosine x over 2x minus pi. So cosine x over 2x minus pi. And now I want to use my table. I want to use my table. So I don't know if you guys remember that. I'm pretty sure I showed you this once before. I'm going to make my independent variable. I'm going to set it to ask. Because then when I go to table, I can just plug in. So I can plug in something like pi over 2. What did I put there? Minus 0.1. Bam. Pi over 2 minus 0.01. Bam. Right, and basically it's already at the answer. Right? I showed you this, I'm pretty sure. Now again, when you do this and it gets a little too roundy, you might want to go do it on this main screen, right? But the table is beautiful in the calculator for getting an idea really quickly. I can just put my own numbers in there and make it do what I want it to do. Is that decent for that? So you could just round pi over 2 to a decimal and then just get closer to that decimal, or you could do this. It doesn't really matter.
So the next step would be to do the positive version
Yeah,
of
yeah,
that, and then see where they come together as the limit. Is that what the question is asking?
Yep.
Okay.
So come at pi over 2 from this side, come at pi over 2 to this side, and then try to make a guess as to where it looks like it's going. Kick ass. You could also, of course, just graph the damn thing. Let's see. See how long it takes this. There we go. And I'm curious about pi over 2. So let me zoom in around pi over 2. Yeah. Yeah, and if I trace this sucker, pi over 2 is like 1.57. Weehaw! You can see it. I mean, you can see this, right?
Mm-hmm.
So the minute I'm right there, I'm really close. Oh, I'm really close, and then I'm further away, further away. Anyway. Right. Okay. You missed all that, but that's all right. Yeah.
I have a conceptual issue with 2.6, the infinities. On the homework online, it was a lot of positive infinity and negative infinity answers.
Oh yeah, same thing with the book.
So there's certain assumptions, I think, that are being made that we should know that I don't know.
So which one are you looking at?
Like, for example, number 12 on the online homework was the limit as x approaches negative infinity, x to the 4th plus 2x to the 7th.
Like that?
Yeah, in parentheses, but yes.
Okay. Yeah. Super. Okay. So what's happening if you let x get really big negative? What's this piece going towards?
That's the problem. I just can't visualize it just by looking
No,
at
no,
it.
no. No visualization. What happens when you raise any real number to a 4th power? It becomes
Bigger. Exponentially bigger?
sure, but it becomes positive is a key thing. Compared to this guy,
Okay.
if it's negative, it's going to stay negative.
Okay, but if it's positive, it'll be infinitely, so that's, you know what I mean, like, how do you, but it's telling me x is approaching negative, so I should assume that there's a negative in there somewhere?
Yeah, it's approaching negative infinity, so you're putting bigger and bigger negative numbers. So the
Okay.
form this is approaching looks to be infinity plus, negative infinity, really, right?
So you can assume that just based on whether it's even or odd, exponent? You can just always assume.
No,
that
there's
the
no
name-
assumption being made. What's negative 1 to the 4097th power?
It'll be -1.
Yeah, see, there's no assumption. It just is.
But it could be positive, is what I'm saying.
Could this be positive?
If X is positive,
Is X positive? What do we know X is doing?
it's going to the negative. So it has to be negative.
Yeah.
So the odd has to be.
So if you're talking about positive X's, you're not doing what this thing is asking you to do. It's asking you to get really big negative.
Okay.
So if you're putting 2 in there, you're nowhere near what this guy is interested in.
Okay.
So all the numbers you're plugging in are really, I used to call big freaking number but negative, right?
So if it was going to the positive infinity,
Yeah. Then this would have been infinity plus infinity. That would have been an easy answer.
which would have been infinity.
This answer is more complicated. This
Okay.
is a type of indeterminate form.
Okay.
Sort of. Which one is going to their infinity faster?
To the 7.
Yeah, this guy's going to their infinity faster, so that's going to overwhelm this. It's sort of like 2 minus 4, 3 minus 16, 4 minus 64, right? This is going to positive infinity, this is going to negative infinity, but the difference is definitely going to negative infinity because the negatives are getting bigger faster. That is actually a beautiful way to answer this question.
So you can skip all the work then and just assume it's negative infinity.
Yeah, I like to say, if they don't say create a table of values, I would rather not.
Well, it has you doing it and like factoring out the x to the 7th and like it just goes on and on and on to get to the negative
I-
infinity. So it's confusing when you can just look at it and have the answer.
Yeah.
Okay.
So I've discussed the idea of comparing rates of how quickly they're going somewhere, so you can start to build off of that. So if you didn't understand the whole thing about the rates, then you could fall back on what they're doing. And really, if you look at, we did an example in here with infinity minus infinity. Where'd you go? Yeah, example 10 in the book. That's really what they're doing. Is you're doing exactly what example 10 does in the book, but a much more interesting way to do it. I always like to say the more you know, the less you have to do.
I would love to get to that point.
Yeah, but it's if you don't know the rate stuff, there is a way to do it. Example 10 in the book is the way to do this kind of problem by the book. But there's an idea of how quickly they're going to their respective things that makes this much faster. Yes,
So is the answer negative infinity?
yes. Cool.
In the book, example 12, it gives you this whole thing about, here's all the info, now draw the graph.
Yeah.
I get where to put the points and all of that through that problem, but then it was more confusing in terms of where to draw the lines at that point.
All right, example 12 is something you did a lot in pre-calculus. When you had to graph something like this, you guys remember when you had to graph something like this, you had to find multiplicities. Anybody remember multiplicities? Multiplicities. Well, some of you guys are like, I'm not going to look at them. Okay. Your teacher might not have told you about multiplicities, but they should have. Holy shit. But what else do you have to worry about? What's the very first thing you had to describe when you went to graph this in pre-calculus? You didn't even talk about the intercepts or anything yet. The first thing you should have talked about was end behavior. How does end behavior relate to stuff we've done? What is the end behavior of this? What's the largest power if I multiply this shit out? And you don't multiply it out, but what would the highest power be? No. Yes.
Oh.
Wouldn't this have an x squared times an x cubed, so x to the 5th? So what's this end behavior going to be? Cubish. What is this? Limit as x goes to infinity of the function. What is this? Limit as x goes to negative infinity of the function. And do you see how example 14, or example 12, that's like the first thing they do? That's the end behavior. So that is just a pre-calculus idea. Everything in pre-calculus related to horizontal asymptotes or what happens when x gets really big is just one of these infinite limits. Your teacher might not have shown you this notation, but now we know that's what it is. That's why I like the teachers that do show this notation, because you're getting you really ready for calculus, which is the purpose of pre-calculus.
So along those lines, if the limit was as x approaches positive infinity, arctan e to the x, do you just look at that and know that arctan is negative pi over 2 to pi over 2?
Yeah.
And just know that since it's going to positive, it'll be the positive pi over 2?
Yeah, because what's the inside? The really important question is, now this kind of seems trivial, but what's the inside doing? It's going to
zero?
infinity.
Or, oh, okay.
Right, it was e to the positive x and the positive infinity, right?
Yeah,
Right.
I need to review my e's.
Well, e is just a number like 2 or 3. It just happens to be in between 2 and 3, but it's just a number. That's all e is. That's it. So when I raise some number to a bigger and bigger power, it gets bigger and bigger.
Oh, I see.
Yeah, that's all. And so you do need knowledge of what the hell that thing looks like. Yeah. So that's what might be frustrating to you guys is you might not know, looking at a problem, what it is that I'm supposed to know already that would help me get through this problem. That's when you go get some help. Right? That's when you ask somebody. But the more you know, and so many of these problems, it's got to do with the shape of the function in the problem. Like natural log, domain and range, that kind of stuff. And I keep saying that's one big thing pre-calculus is supposed to do, is just hammer in your head the shapes of all these functions.
So another question along these lines that it just gets a little more complicated for me visually. So its limit as x approaches infinity, and then it's e to the negative 2x times cosine x. Yeah. So I know that cosine x is negative 1 and is less than cosine x is less, less than,
okay.
Is it less than or equal to 1? But then where do you
What do you want in
thoughts
here?
go?
What do you want here? Where's what?
0?
No. What function is the question asking you about? This one.
Right.
Have I written anything down about that function yet? No. What's missing here so that I have that function?
E to the
Yes, let me multiply everything by. Now I know the bounds of the function they're actually asking me about, right?
Oh, okay.
And then what's the last thing that's missing in the question? It wants me to do what to that function?
Go to infinity. So
Take
then
the
it
limit.
has to be positive.
Hmm?
So then is it positive infinity?
No, now you take the limit of everything.
Oh,
And what is e to the negative 2x doing as the exponent gets bigger and bigger? As the x gets bigger and bigger. E to the negative. See, this
But
is
it's
kinda,
positive because it's negative and negative, right?
what do you mean? No. This negative can't do shit to that negative. Right?
Okay.
That can't suddenly hop up there. There's no
Okay.
freaking way.
So it just is an increasingly negative number?
No. What does e to the negative 2x mean? What's a better way to kind of write that without the negative power? What's the negative power mean?
It's
Four-letter
a
word starts with
fraction.
F. You can say in mixed company.
1 over 2?
Flip. Flips.
So it's negative 1/2 x?
Hell no. What's being raised to a negative power?
E.
There you go. So it's 1 over e to the 2x. So negative 2 doesn't equal 1/2. That never ever was true.
Okay.
Right? You can't learn something that goes against something you learned before. Ever. So what does this do? When x gets really, really big, the bottom gets really, really
Small.
No,
Big.
big, right? You gotta, don't try to guess where I'm going with the pattern of my
That's
question.
what I'm asking for help. I don't.
Well, right there.
Okay.
E to the really freaking big is extra freaking big.
Right, okay,
So what is 1 divided by really freaking big?
big,
1 divided by really big.
okay, small.
Small. Well, come on. 1 over 10, 1 over 100. As the bottom gets bigger and bigger and bigger, the whole thing goes, it's smaller,
Okay,
smaller, smaller.
okay.
So this limit is 0. This limit is 0. So what must this limit be? If that lives between 0 and 0, it must be
Infinitely small.
0. The limit is 0.
Okay.
I agree with you in a sense. This never gets to 0. This never gets to 0. But what's the limit as x gets big? The limit is 0.
I get it, but I'll have to work on it.
What piece?
It just conceptually, I'll just need to work on it.
Okay. So it's just like 1 over x. What happens to 1 over x as x gets really big? Gets smaller, smaller, this is 0. Right. In fact, we use that fundamental idea to help us with limits of rational functions and stuff like that.
Five on the practice.
Oh, that's this here. Same idea. So you would start with the sine piece, sine of 3 over x minus pi in between these two, multiply all the sides by the x minus pi cubed, take the limit, yeah. So the basic idea of the squeeze theorem is to start with the thing that's bounded and then build on that, yeah.
Six.
So on 6, what is the most important point to be careful about on number 6? What kind of functions are continuous? It's a really good idea to know. Page 120, theorem 7. So what functions are continuous? Polynomials, obviously, that's their defining quality. Rational functions on their domain. Trig functions on their domain. Inverse trig functions on their domain. Exponential functions, logarithmic functions on their domains. Those are all continuous on their domain. So number 6, what's true about 2 cosine 3x? Is that function continuous? Yes, it's a trig function, and its domain is everything. What about negative 6x over pi? Is that continuous everywhere? Hell yeah, it's like 2x. Do you guys see that? Negative 6 over pi is gross times x, so that's beautiful. That's continuous. It's the most basic polynomial, right? So those two by themselves are continuous, whereas the only place that the whole thing could be discontinuous, yeah, pi over 3. If this guy sets up an open circle that this guy doesn't fill in, it's discontinuous there. So the only place you have to check is pi over 3. Well, how do you check it? What do you do to check this to make sure that they fill each other in? Oh, on this Valentine's Day. How do you check to make sure that these guys don't miss each other and don't have a happy life together?
What chapter is this? Or what section?
It's on the test, on the practice. Huh? Yeah, I think I heard somebody say it. Say it again. Plug it in.
No,
That's
I'm
it.
just wondering what chapter.
Where's he go at pi over 3? Now, one thing you could say is, well, he's not allowed to go